Yes, sir.
Yeah. In the last class, we were discussing regarding the design optimization problem formulation. So I think we started with different concepts of design formulation, different procedures, and everything we just started in the last class. And also we started with some of the problems also in the last class. Today, let us continue with the same thing here. So I hope in the last class, I just started with this problem, minimum weight tubular column design. So I think I have given a solution for this also. I hope you have understood. I think you have two formulations for this problem. So the diagrams I have shown here is the first formulation is with the mean radius 2r and the thickness t. And I ask you to just get the solution for the second formulation in terms of R naught and R. Okay, quickly I will go through this. So strike members are used structural elements in civil, mechanical, aerospace, agricultural, and automotive structures. Many such applications can be observed in daily life, for example, street light pole, a traffic light post, or a flag pole. It is important to optimize the design of a strike column since it is mass produced. The objective of this project is to design a minimum mass tubular column of length L supporting a load P without buckling or overstressing. The column is fixed at the base and free at the top as shown in the figure. The structure is also called as a cantilever column. I hope everybody is having a paper and a pen. So please just go through and just keep on just noting down what are the things I'm going to discuss. And at the end, I will give one or two problems for solutions to get the ready with the solutions in the end. Okay. I'm just muting all you people. Afterwards, I will just come back to you. Yeah. So this is the data and information collection. So we have buckling load for cantilever column, crippling load by square EI by 4L square. The buckling load formula for a given column with support conditions is different from this formula. Here I is the moment of inertia for the cross section of the column and E is the material property called modulus of elasticity. Note that the buckling load depends on the design of the column. It imposes a limit on the applied load. The column fails if the applied load exceeds the buckling. The material stress sigma for the column is defined as P by A, where A is the cross-sectional area of the column. The material normal stress under the axial load is sigma A, and the material density is. So this is what I was talking in the last class. I think I discussed this in much more detail in the last class. I just rush up for these things because I want to give the second formulation for this problem. And cross section we have shown there. This is the cross section of the minimum weight tubular column. Okay, so we will be starting with the first formulation by taking mean radius 2r and thickness, wall thickness t, and taking this we will go into formulate the optimization problem. So this is the one. So formulation 1 for column design, definition of design variables. So first, please we can note of these things. This design variables is very important here. For this first formulation, the column design variables are defined. So R is the mean radius of the column and T, it is wall thickness. It should be small t actually, by mistake it is capital T, it should be a small t, wall thickness. Assuming that the column wall is thin, R should be much greater than that of the thickness. The material cross-sectional area and the moment of inertia. A is equal to 2 pi R into T, and the moment of inertia I is equal to pi R cube. It is read it as a pi R cube times T. So this is the formula for calculating cross-sectional area and the moment of inertia. Please make a note of these things quickly. And the optimization criteria in this problem is the total mass of the column to be minimized as given. Mass is nothing but the density into volume. So mass is given as is equal to the rho into L into A. Rho corresponds to the density of the material of the column, and L into A corresponds to the volume of the column, and which we will go to write it as 2 into rho into L into pi into R into T. So this is the optimization criteria because the weight is mass is directly proportional to the rho and volume. And coming to the constraints here, the first constraint is that stress P by A should not exceed the material allowable stress sigma A to avoid the material failure. To avoid the material failure, so the value of sigma by A should not exceed the allowable stress value. So this is one of the first constraint here is the column should not buckle due to the excess stress. So inequality sigma should be, that is the stress, induced stress should be less than or equal to the allowable stress value. So therefore, P by A, sigma replacing P by A and substituting P divided by 2 pi R into T should be less than or equal to the sigma A. This is the first constraint for us. Please simultaneously, please keep a note, noting on all these things. This is very important for the formulation of design optimization. Right? And the column should not buckle under the applied load P, which implies that the applied load should not exceed the buckling load. Using this expression for the buckling load and substituting for I, so we have P should be less than or equal to pi cube into E into R cube into T by 4L square. So this is the crippling load formula because column fails by two times. One is by crushing, another one is buckling. The first one, what we have taken it as we are crushing, and second one, the type of failure that column may undergo is due to a buckling, and hence the buckling load, the stress or the applied load should not exceed the buckling load or a crippling load. So therefore, P is the applied load, and P suffix CR corresponds to the buckling load or a crippling load. So therefore, this is the second constraint. Please keep a note, keep on noting all these formulae. This is how we will go to formulate the constraints, objective functions, and the design variable. Finally, the design variable R must be within the specified minimum and maximum values. So the R value, what we are showing here is, so you can just note it down. My dear students, are you following me?
Yes, sir.
Please keep a note of all these things because it's very important. So at the end of this class, you will have to solve two problems for an assignment. So please keep a note of that and keep just observing. If any clarification, you can just ask me at the end. Okay. Please make a note of, if you have any doubts, please note the slide number. Slide number is there. Please make a note of the slide number. If you have any clarification, so we can discuss at the last 10 minutes. We're going to discuss everything. So this is the first formulation. I was in the last class, I was just given one simple assignment just to try with the second formulation where we will go into express the design variables and the objective function as well as the constraints in terms of the Ri and R0, where Ri is the inner radius of the column and R0 is the outer radius of the column. Okay. So that picture what I have shown here. So this is the second formulation I was talking about, the Ri and R0. So I want to formulate the optimization problem with respect to this Ri and R0. So what we completed in the first formulation is with respect to R and T. Now we want in terms of Ri and R. Only the small changes and modification that needs to bring to the formula in the cross-sectional area as well as the moment of inertia. So rest of things will remain same in the second formulation also. Let us look into that also. Second formulation I will take here. So in the formulation 2 for the column design, please keep a note of all these things one by one. This is the second formulation. Step number 1 and 2 remains constant, remains same, and from third step only the formulation 2 starts. Okay. The another formulation for design problem is possible if the following design variables are defined. If R0 is the outer radius of the column and Ri is the inner radius of the column. So here we have R0 and Ri, the two radius of the outer radius of the column, and Ri is the inner radius of the column. In terms of these design variables, the cross-sectional area A and the moment of inertia I. So please, small changes, what you're supposed to do, A is equal to pi R naught square minus Ri square, it is, or Ri into Ri, and I is pi by 4 into R naught to the power of 4 minus Ri to the power of 4. I think this formula are already familiar for you people, right? So this is A is pi into R naught square minus Ri square, and I is equal to pi by 4 into R naught to the power of 4 minus Ri to the power of 4. Please bring, just make a note of these things changes in your, when you are writing it down. This is step number 3, defining the design variables. And step number 4, we have optimization criteria. Same change, to minimize the total mass of the column, mass density into volume. So here pi into rho into L, and R naught square minus Ri square. The only changes what I have just remembered. Instead of R and T, so we have here R naught and Ri. And coming to the step number 5, formulation of constraints. The material crushing constraint, that is P by A should be, P should be, sigma should be less than or equal to allowable stress. Same formula. Only thing, we have changed the formula in terms of R naught and Ri. Using the foregoing expression I, the buckling load constraint. So please, these are changes what you're supposed to bring it out when you are changing the formulation. See, in the examination, they don't specify whether which type, first one or second one. So you can do any one of these formulations. This is asked for minimum 6 to 8 marks in your exam. So either you can take the mean radius and thickness, as well as or you can use R naught and Ri, and you can do the formulation for this type of. Okay. So this is this step number 5, and the constraints again. So same thing. R naught minimum Ri and R max. Ri minimum should be less than Ri, or should be. When this problem is solved using a numerical method, Ri should also be imposed. Otherwise, some methods may take the design footprint where R naught is greater than Ri. This situation is not physically possible and must be explicitly excluded to numerically solve the design. So this is regarding the problem number 3, where we have two different formulations. Okay. Yeah. Any doubts, students? Because please make a note of these things. If you have any clarifications, you can make it before I just switch for the next problem.
Yes, sir.
Danush, can you hear me?
Yes, sir. Yes, sir.
Yes, sir. Please, I will could you able to note it down?
Yes, sir.
Mithun, are you there?
Yes, sir. Yes, sir.
Danush, Mithun, Sukrut.
Yes, sir. Yes, sir.
Please make a note of all these things. Okay, I will going to start with a new problem, the fourth problem now. Should we go ahead for 4?
Yes, sir.
Please make a note of this problem. This is the most important problem from the examination point of view. Please make a note of the next problem, that is sawmill operation problem. I want everybody to note down this problem. Quickly. A company owns 2 sawmills and 2 forests. A company owns 2 sawmills and 2 forests. The table 2.1 shows the capacity of the mills, logs per day, and the distance between the forest and the mills in kilometers. Each forest can yield up to 200 logs per day for the duration of the project, and the cost to the transport the logs is estimated at $10 per kilometer per log. At least 300 logs are needed daily. The goal is to minimize the total daily cost of the transporting the logs. Please make a note of this problem. This is step number 1 statement. Please read the problem properly. The company has 2 sawmills and 2 forests because it is a sawmill operation what we are optimizing here. A company owns 2 sawmills and 2 forests. I will next slide. We have a table. 2.1 shows the capacity of each mills per day and the distance between the forest and the mills in kilometers. So the capacity and the distances between the forest and the mills will go to show it in the table. Each forest can yield up to 200 logs per day. The capacity of each forest is 200 logs per day, and the cost to transport the log is estimated. So to transporting the logs from forest to the mills is $10 per kilometer per log. Means transporting one log over a distance of 1 kilometer, it costs $10. That is the meaning of this. And at least 300 logs are needed daily. The company needs 300 logs. The goal is to minimize the total daily cost of the transporting the logs. So this is the project or a problem description. I think from this only you can easily understand what is the objective function. Okay, so let us go one by one. Now let us go to the step number 2. Will we go to step number 2? Will we go to step number 2?
Yes, sir.
Okay. Yeah, let us go to the step number 2 now. So sorry, this is please make a note of this data. Table 2.1 was here. If the distance is mill is given A and B. Distance from mill A, it is mill A actually, mill A, and distance from mill B, this is not 1 and 2, it is. Distance from mill A. Hello.
Yes,
Yes,
sir.
sir.
Please small change here. This is distance from forest 1, this is mill 1, not mill 1, it is forest 1, and this is distance from forest 2. Distance from forest 1, distance from forest 2, this is. Please make a note of that. And mill capacity per day is 240 logs for mill A and mill B. So small changes what you're supposed to bring here is mill 1 here, make it as forest 1, this is mill 2 is forest 2. And rest of things are same here. Yeah. I will go to the next step now. Can I go?
Yes, sir.
Can I go to the next step?
Yes, sir.
Yeah.
Yes, sir.
Yeah. So step number 2, data and information collection. Data are given in the table and in the problem statement. So no data and information collection over here. Step number 3 is definition of design variables. The design problem is to determine how many logs to ship from the forest I to the mill J, as shown in the figure below. Therefore, the design variables are identified and defined. See here what's happening. We have 2 forests and 2 mills. Each forest will go into supply the logs to the each mill. Okay, so the distance between the mill and the forest they have given, the capacity of the mills also they have given. Okay, the corresponding forest, what is the distance from forest 1 to mill A and forest 2 to mill A, and forest 1 to mill B and forest 2 to mill B. So this is what the table, what it shows, the distances between the corresponding mills and the forest. Now what we want to do here is, we want to formulate the optimization design problem for optimizing the transportation cost. So because for transporting a one log from one forest to the mill, it costs $10 per kilometer. So distance we know. So how many logs it will going to produce we know. So now what we want to do is, we want to get what is the design variables over here. Okay. So I'll just draw the diagram here. Look at this diagram here. So forest 1, forest 2, mill A and mill B. Here, so this is the forest 1 and this is the forest 2, and X1 and X2, X3 and X4. So these are called the design variables for us. What actually this X1, X2, X3 and X4 corresponds to? The number of logs, so it is there, the number of logs shipped from forest 1 to mill A. The number of logs shipped from forest 1 to mill A is number of logs shipped from forest 1 to mill A is X1. Okay. Number of logs shipped from forest 2 to mill A is X2. Similarly, the number of logs shipped from forest 1 to mill B is X3, and the number of logs shipped from forest 2 to mill B is X. So X1, X2, X3 and X4 corresponds to the number of logs which are shipped from each forest to the each mills. So this is the diagram, what it will go into, give clear picture of the design variables. So if you draw these diagrams, please draw these diagrams and just indicate what is X1, X2, X3 and X4, then things will become very easy. Why I'm talking this is a very important problem in the examination point of view. Okay. So here I am just explained here. X1, number of logs shipped from forest 1 to mill A. X2 is the number of logs shipped from forest 2 to mill A. X3 is the number of logs shipped from forest 1 to mill B, and X4 is the number of logs shipped from forest 2 to mill B. Please make a note of these things. And note that if we assign the numerical values to these variables, an operational plan for the project is specified and the cost of daily log transportation can be calculated. The selected design may or may not satisfy all the conditions. In the sense, so if we assign the values for X1, X2, X3 and X4, okay, we can easily calculate what is the transportation cost, the daily transportation cost for the company, because company has 2 mills and 2 forests, and we know what is the capacity of each mill and what is the number of logs which are shipped from each forest to each mill, that is in the terms of design variables. Okay, we know what is the cost for shipping a one log over a kilometer. So all these things put together, we have to frame a objective function, which is nothing but the cost function. So here, the cost function is to be minimized. The ultimate objective of this optimization is to minimize the cost. So therefore, now we have to write what is the objective function, which is a minimization of the cost, minimization of the cost of daily transporting the log. Okay, so how it can be written? Okay, this I will going to put it in the next slide here. See, this is the one. Step number 4, optimization criterion. The design objective is to minimize the daily cost of transporting the logs to the mills. the cost of transportation, which depends on the distance between the forest and the mills, is. So you can see the cost is equal to the cost function we have written here, which is equal to 24 into 10 into x. What is this 24 into 10 into x1? This corresponds to. If this corresponds to the cost of transporting the total number of logs from forest 1 to mill A. See, what is this 24 and 10? The 24 is, you can see here, the distance. The distance from mill A to the forest 1 is 24. Okay, so 24 into 10. What is 10? It is the cost which is incurred for transporting over a 1 kilometer per log. So 24 into 10 into the number of logs. Number of logs shipped from forest 1 to mill A is x1. Okay, so here we have taken the 24 is the distance from the forest 1 to mill A. 10 corresponds to the cost of transportation per kilometer per log into x1. x1 corresponds to the number of logs shipped from forest 1 to mill A. So this is what we call it as 24 into 10 into x1 is the total cost incurred for shipping the x1 number of logs from forest 1, which is at a distance of 24 kilometers from mill A. So this is for the shipment of a log from forest 1 to mill A. So like that, so we have three different cases over here. Let us take the second one, plus 20.5 into 10 into x2. What does this corresponds to? 20.5, the first term corresponds to the distance. Please remember this. First one corresponds to the distance. 20.5 is the distance between the forest number 2 to the mill A. So you can see this table here. The distance from forest 2 to mill A is 20.5. So 20.5 into 10 again, the cost for shipment of log for 10 per 1 kilometer into x2. What is x2? It is the number of logs shipped from forest 2 to mill A. So this corresponds to the total cost, total transportation cost incurred for shipping the x2 number of logs from forest 2, which is at a distance of 20.5 kilometers from mill A. So this is how we have formulated the cost function. In a similar way, when you take 17.2 into 10 into x3, this is for second, that is mill B. This is 17.2 is the distance from forest 1 to mill B, and x3 is the number of logs shipped from forest 1 to mill B. Similarly, 18 into 10 into x4. 18 is the distance from the forest 2 to mill B, and x4 is the number of logs shipped from forest number 2 to mill B. So this is what we call it as the total cost function. So in our optimization problem, we need to minimize this optimum function. Of course, this is just multiply this. This is totally what we have got, the total cost function. Please understand this. This is very important. And the next number, that is step number 5. Formulation of constraints. The constraints for the problem are based on mill capacity and the forest yield. So we have 2 mills and 2 forests. So forest mills have their capacity and the forest they have their yields. So everything it is specified in your table only here. So you can see the mill capacity is 240 logs per day. and for mills, for mill B, it is 300 logs per day. Okay, and here what it says, minimum 300 logs required, and each forest can yield up to 200 logs per day. So this is the one capacity is what you're supposed to be very careful while you are drawing or when you are specifying the constraints. So here x1 plus x2. So the number of logs which are shipped from forest number 1 to forest number 2. This is the mill capacity I am talking about. Mill capacity, it can take only 240 logs from both the forests. So therefore, x1 plus x2 should be less than or equal to 240. And here x3 plus x4 or x3 plus x4 should be less than or equal to 300. This is the mill capacity of D. And the forest yields, because the minimum yield of the forest should be 200, what they have specified. X1 plus x3 should be less than or equal to 200, and x2 plus x4 should be less than or equal to 200. So this is the 4 different constraints. Here you just make a note of here, it is x3 plus x4. It is not x3, and just by mistake I just did it as x3. x3 plus x4 should be less than or equal to 300. So this is the capacity, mill capacity, what is supposed to enter over here. So this is the constraints what we have. Apart from that, we have another one constraint, that is constraint on the number of logs needed for each day is expressed as x1 plus x2 plus x3 plus x4 should be greater than or equal to 300. This is the demand for the logs. That is, minimum logs that needs to be shipped is 300. So therefore, the total number of logs per day from both the forest and for both the mills should be minimum of 300. So therefore, the another constraints what we can put it over here is x1 plus x2 plus x3 plus x4 should be greater than or equal to 300. For the realistic problem formulation, all design variables must be non-negative. That is, xi should be greater than 0, I should be equal to 1 to 4, because another one constraint what you can put it for realistic problem formulation, x value, that is the design variable, should be always greater than 0. The problem has 4 design variables, 5 inequality constraints and 4 non-negativity constraints on the design variable. Note that all the problem functions are linear in the design variables. So this is a linear programming problem. Note also that for the meaningful solution, all design variables must have integer values. Such problems are called integer programming problems and require special solution methods. It is also noted that problem of sawmill operation falls into the class known as transportation problem. For such problems, we should like to ship items from several distribution centers to several retail stores to meet their demand at a minimum cost of transportation. So this is the problem for the sawmill. Okay. So if you have any clarification, we will have that. We will discuss that. Yeah. Anybody have any clarification? I will just give 1 minute time. Any clarification in this slide? Students, any clarification anywhere?
No, sir.
Please make a note of this because I am running out of time. I will give another 2 problems for assignment. And any clarification, please discuss me. Please make a note of these things. It's very important. Okay. I will give you the problems for assignment. Please make a note of this quickly. All of you. Please make a note of this. I will read out quickly. A 100 into 100 millimeter lot 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 is available to construct a multi-story office building. a multi-story office building, at least 20,000 meter square of total floor space, 20,000 meter square total floor space is needed. Is needed according to zoning ordinance. The maximum height of the building can only 21 meters, and the parking area outside the building must be at least 25% of the total floor area. It has been decided to fix. It has been decided to fix the height of each story at 3.5 meters. The cost of the building in millions of dollars is estimated at 0.6 h, small h, plus 0.001 times a. So I'll repeat once again, 0.6 times h plus 0.001 times a, where capital A is the cross-sectional area of the building per floor and h is the height of the building. Formulate A is the cross-sectional area and h is the height of the building. Formulate the minimum cost design problem. Formulate the minimum cost design problem. I will put this assignment in the Google Classroom also, okay, so that it will be easy for you to understand and you can solve it and you can get ready with the solutions. You will be expected to put it in the Google Classroom or you can expect it to submit it to me later. Okay, another one problem is there because I'm just running out of a time. If possible, I will just put it in the classroom. Please make a note of that also. Okay, Google Classroom. Okay, so any clarification, students?
No, sir.
Are you able to follow what we are talking here? If you are finding any
Yes, sir.
difficulties, are you finding any difficulties? Please, you can come up. You can come up at any time. You can talk to me. Okay, because during each class, if you want any other sessions for only clarifications and anything, you can post it. So we can do that part also. No problem. Because the module 2 is very, 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 very important for you. Problems are there because it looks very simple, but you need to apply very clarity. Clear should be there. Otherwise, it's very difficult for you. Okay. So please try to solve that problem. So if any have clarifications, you can have under just 20 seconds upload for me. Okay, then we will meet day after tomorrow for the next class. Okay.